Hi, my name is Vinayak, and I'll be presenting work about linear hashing. This is joint work with Michael Jobber and David Zuckerman. So let's consider a classical scenario where we're tossing n balls uniformly and independently into n bins. The question is, what is the number of balls in the heaviest bin? A classical result in probability says that the average value of the average weight of the heaviest bin is at most log n over log n balls. This classical result in probability is very useful in theoretical CS, especially in randomized algorithms and hashing. I'll now discuss the application to hashing. So in hashing, we're usually trying to hash a very large universe, say n to the 100 elements, to just a small number of bits, like n bits, and we want to minimize the number of collisions. So let's say our hash is just a uniformly random map taking u elements to n elements. And now let's say we have a set of n balls in our universe, n arbitrarily picked balls. Pictorially, we can think of this vast C as our universe, and then some random blob in it, some arbitrary blob is our set S. So we can think of H as partitioning our universe into n bins by its preimages. So in particular, a random H, it'll randomly partition it into some maybe weird looking parts, where each part's defined by all the universe elements that map to a particular value. Right? So we can see in this diagram, each region corresponds to all the universe elements that map to a particular value. So this is all the ones that map to 1, the ones that map to 2, so on. So this will split up the balls, right, the dark blue region, up. And our goal is to minimize collisions, which means we want not too many balls to be in each preimage or each bit. So in particular, I can define the load of y, the load of the yth bin, to be simply the number of points in S, the number of balls that map to y via the hash function. Right? So this is going to represent how many balls are in the yth bin. And then I can define the max load to just be the maximum number of balls in any bin. So the max over y of the load of y. In this picture, this part has the most of S, and so this is going to be. And so the max load will be how much of S is in this part. So one thing I want to say is that H must be random. If H was one fixed function, then we can argue by an averaging argument that if I partition n to the 100 elements into n parts, there must be one part with at least n to the 99 universe elements. I could then just pick n out of those n to the 99 elements to be my set of balls, and then suddenly there's one part with all n balls in it. So in particular, I can adversarially pick an S so that for any fixed H, so for fixed H, I can adversarially pick an S that'll have max load n. On the other hand, if we use randomness, by the first slide, we can actually show no matter which n balls you pick, a uniformly random hash map on expectation will have max load log n over log n, even with an adversarially picked set of balls. That's great. So what more is there to do? Random does amazing. Well, the issue is that a random function is very expensive, both in terms of space and time complexity. How many maps are there mapping u bits to n bits? Sorry, u elements to n elements. There's n to the u such functions, and so it'll take u log n bits to specify, which is way too much. Furthermore, a random function with high probability will be hard to compute, say by a Shannon argument. Therefore, this begs us to ask the question, what's the simplest hash family with optimal max load? Is there one that we could say implement and have it run quickly? So this question's a bit vague, and there's honestly two ways of thinking about it. One is a purely engineering-based approach. What is that? It's to think of the time and space complexity as like parameters you want to minimize. You're sort of video gaming. And so you want to design using any tricks necessary, some hash function that'll take up small time and space complexity, say using the word rem. So this actually got us very far. So actually the best constructions has log n times log n space complexity and log n squared time complexity. So these are within a polylog n factor of optimum. The drawback is that because you used any trick necessary to get those hash functions will usually be hard to implement, or in practice, they'll take many operations to run. So in particular, these constructions, they're going to use lots of finite field multiplications and lots of like polynomial modular arithmetic and various other operations that are quite tricky to implement. So another way to go about this problem, sort of to capture this drawback of this approach, is to first fix a construction, like maybe find a construction that is practically feasible, and then ask, okay, what's the max load of this hash function without changing the hash function anymore? So this will obviously yield much simpler hash functions since we're forcibly keeping our construction to be simple. And there's been progress here as well. In fact, maybe a nice result is that there's a simple way of hashing called tabulation hashing. And Petruscu and Thorup were able to show that these have optimal max load along with other hashing properties that are ideal. So more or less, how this hash function works is you take your input, you split it into constant many blocks, and then you're going to have hard-coded for each block some hash table that'll map it to some smaller string. And then what you do is you XOR all of these, all of the hashes of the blocks together. So this will take just constant evaluation time because there's a constant number of blocks. But then encoding each hash table will require n to the epsilon space, which is not so ideal. But in terms of practicality, it turns out you can sort of make this fit into the fast cache. So what we're going to look at in this talk is something that's even simpler than tabulation hashing. It's basically tabulation hashing without the hash tables. And this is just linear maps. Okay. So what do I mean by a linear map? Well, all I mean is a random matrix over F2. This type of hash function dates back to Zobrist in 1969 and was formally introduced in the first paper on universal hash as an example of a simple universal hash function. So this map concretely, let's say I rearranged my U element universe into a vector space of dimension log U, and I rearranged my n bins into a vector space of dimension log n. So here, big U equals 2 to the little u, and n equals 2 to the L. For the rest of this talk, L is going to denote log base 2 of n. Now that I've rearranged it, so I've more or less added some algebraic structure to these discrete sets. I'll now think of my hash map as just a random linear map from F2 to the U to F2 to the L. That's it. So one way of thinking about this is a random matrix, right? So I can think of sort of storing U columns, C1 through CU. And then X is just going to map to the left matrix multiplication against this column matrix. Or in other words, X will map to the sum of the columns corresponding to where X sub I is equal to 1. So what this tells us is first, the storage of this hash function is simply log n squared, right? Because that's how many bits are in this matrix. And then second, we will only do up to log n many XORs in order to evaluate our hash function. So there's no finite field multiplication, no modular arithmetic. It's all just XORing strings together. So another way I want to introduce hash functions is back to the pictorial definition. So here, we're again partitioning the universe, but now we're using the fact that a linear map, its kernel, so all of its preimages are just shifts of the kernel. So in other words, all preimages are just going to be shifts of some subspace. So you can think about a linear map, a hashing of using linear maps as the following. I pick a random subspace, and then I tessellate the universe with shifts of this subspace, and that's my hash. And then so I can now ask, if I pick a random subspace, tile the universe with this subspace, will any S be spread among such a partition? Is such a subspace partition pseudo-random? Great. So let's ask what we know about the max load. So first, let's get the lower bound out of the way. In terms of the lower bound, any hash family will have expected max load at least log n over log n, no matter how many functions are in the family and no matter what the functions are. Now, in terms of upper bounds, in the paper that introduced universal hash functions, they proved that any universal family has max load root n. Linear maps are universal, and so they have this bound. A year later, along with Markowski, they showed a polynomial improvement on the max load from square n to n to the 1/4. Some years after that, Melhorn and Vishkin were able to show a sub-polynomial bound on the max load of linear maps. And then finally, in 1997, Alon Dietzfeldbinger, Milterson, Petrank, and Tardish showed something very small, just a log n times log n max load. At this point, one probably is asking, can we get optimal? We're like awfully close to log n over log n. Indeed, this question was also asked by Alon et al. What is the right bound? And surprisingly, there hadn't been much progress since then, with the exception of a note posted on arXiv in 2018, where Babka showed that if Alon et al. Had set parameters better, they could have actually gotten a log n max load. So maybe you'll ask, oh, can you set parameters even better to get a log n over log n max load? And unfortunately, you can't, because if you run their argument through a fully random map, that argument will still only yield a log n max load, even for a fully random map. So you need some sort of different argument or different idea in order to hope to get a log n over log n. So the question, is there a log n lower bound? Is it optimal? Or is it something in between? So we answer this question in the affirmative, and we show that a random linear map indeed has optimal max load. And so for this talk, I'm going to attempt to like completely prove a baby result. So what I'm going to show is that for any set, for all sets of n balls, I can then give you one hash function such that the max load with respect to this hash function is optimal, right? Clearly, if the average max load is optimal, then by an averaging argument, there must exist one that gets you optimal. And so we're just going to show this existence portion. So what's the key idea we use? It's potential functions. So the intuition is that maybe your first approach will be to want to like look at the tuple of n loads corresponding to the n bins, and then maybe analyze the probability, like maybe a particular bin has load at most log n over log n, and then union bound over everything. So the issue is that these loads are very correlated. So in particular, as an example, if I know where h of x and h of y is, I know where h of x plus y is because of linearity. H of x plus y equals h of x plus h of y. So in general, balls in linearly dependent positions will create correlations. And so it's going to be hard to analyze the correlations for an arbitrary set of balls. What we do instead is focus on just one real number that'll sort of measure how imbalanced our allocation is. For example, we can consider this following softmax function. It's going to be the average of the exponentials of the loads of the bins, right? The idea is that if one load is large, this quantity is going to be dominated by that term in the sum, and so this value will spike. If all the loads are small, then this quantity will remain small as well. So let's be more formal about this. Let's say I have some arbitrary set of size n, and I want to find some hash function h that equally partitions S. And let's say V is the kernel of H, right? So we're going to construct an H such that with kernel of dimension L, right? With dimension 2L minus L, which is L. And so what we do is we're going to define the potential function of S with respect to H to be the average of the exponentials of the loads. Here, the exponent is not 2, it's log of n. So, of course, load of y is just the preimage of y intersected with s, so we can write it as follows. And then, using the subspace shift, using the kernel definition, we can also write it as the average over all shifts of L raised to the intersection of S and the shift, right? So picking a random preimage is the same as picking a random shift of my kernel, is what I'm saying. And so thus we have this expression as well. Great. So in more formal terms, we want to argue if there exists some y star whose load is large, greater than optimal, then the potential is large. And this is easy to see because just the contribution of the y star term is going to give us a good lower bound. So our potential phi is equal to this expectation, which is at least the contribution of the y star term here. Simplifying this and bounding the load by 4L over log L, we get the following. And then simplifying this, the log L's cancel, and then 2 to the L is n. We'll get n cubed. Thus, we've shown if a bin has larger than optimal max load, then the potential will be large. It'll be greater than n cubed. Writing the contrapositive, that means if we can find a hash function whose potentials is at most n cubed, then we're done. So let's focus on that. Let's try to minimize the potential. But it's not clear that looking at the potential is simplified or prime, right? Given an S, how are we going to find such a function? Well, using the subspace point of view, this is equivalent to sort of finding, we want to find some subspace such that the potential with respect to shifts of the subspace is going to be small. So how are we going to find the subspace? The idea is to sort of find it one dimension at a time. So what do I mean by this? So to get this L-dimensional subspace V, we're just going to focus on picking it one basis vector at a time. So we're going to start with the trivial zero vector space. And then we're going to pick some vector W1 that's not in V0, and then span it with V0. This will get us V1. And then we'll pick W2 not in V1, and then span it with V1 to get V2. And we'll repeat this L times until we get an L-dimensional subspace, V sub L, which is the span of the L vectors we picked, W1 through WL. Now, pictorially, this gives something interesting. So in the start, we have n elements, so these blue squares corresponding to the balls. And if our kernel subspace is just the singleton 0, then shifts of this vector space is just going to partition my universe into singletons, right? Because any shift of V0 is itself a singleton. And so what we have is we have n squared universe elements where each universe element has its own bucket. Now, what happens if we span V0 with W1? So let's say W1 is this following Brown vector. So V0 is now going to be the disjoint union of this bottom left cell along with the cell to the right of it. And so it'll be this rectangle. And so thus, our hash is going to look something like this. Now we're looking at shifts of this rectangular subspace. And so now we have a slightly coarser hash where we've sort of paired up buckets we've paired up bucket X with bucket X plus W1. We continue. Let's say we pick W2 equal to this Brown vector. Then V2 is going to be the disjoint union of this cell along with the cell right above it. And so now we'll get this big square. And so hashing with respect to shifts of the square will look like this. And we do this so on and so forth until we finally get the hash, which is down here. And we're interested in how many balls are in the heaviest shift, affine shift. Right. And then VL is going to be the final kernel subspace. Great. So why have we done all this? The idea is that we're going to keep track of the potential at every time step. So after we add one vector, we're now going to measure the potential, right? Because at each time step, we have some partition of our space. And so thus we can easily define potential with respect to it, right? So in particular, the ith potential will be the average exponential where we pick a random shift. We pick a random shift of V sub I and then see L raised to the intersection of that shift with S. And so thus, we can see that the Lth potential is going to just equal phi. Now, just to recap, we want phi sub L, the final potential, to be at most n cubed. At this point, I can now tell you how we're going to pick our kernel. This is what we're going to do. So notice that phi sub 1 only depends on the choice of W. And in general, phi sub I only depends on W1 through Wi. So what I'm going to do is I'm going to pick W1. So phi sub 0 is a fixed real number. I'm going to pick W1 to minimize the value of phi sub 1. I'll fix W1. I'll now pick W2 to minimize the value of phi sub 2. I'll then fix that. Then I'll pick W3 to minimize the quantity phi sub 3. I'll keep continuing this until I pick WL to minimize the value of phi sub L. I'll now claim that this will give us V sub L that'll have potential at most n cubed. So how are we going to show this? It's by this following key lemma. It says that if we actually just pick W sub I plus 1 randomly among the universe elements not in V sub I, we'll actually get that the expected potential value is at most the square of the previous potential. Okay? So by an averaging argument, this means that there exists a W sub I plus 1 such that phi sub I plus 1 is at most phi sub I squared, right? So I can do this iterative fixing procedure so that the next potential is at most the square of the previous. So this immediately gives us a bound, right? That means there exists some space V, which is the span of these L vectors, such that the final potential is at most the square of the penultimate potential, which is at most the fourth power of the potential before that, so on and so forth, which is at most the 0th potential squared L times. And this is simply phi sub 0 to the n. Great. So now we know there exists some subspace of dimension L such that its potential is at most phi sub 0 to the n. What is phi sub 0? It's actually very easy to compute, right? It's this trivial singleton hash, right? There's n squared buckets. N of them have 1 ball in it. The others have 0. So I can just immediately compute this, right? So I'll have n out of the n squared contributing an L to the first power, and then the remaining contributing an L to the 0th power. And so we can bound this by 1 plus L over n. And now, right, my potential is at most phi sub 0 to the nth, which we plug in our bound is 1 plus L over n to the nth. Using our favorite exponential inequality, this is at most e to the L over n to the n, which is equal to e to the L, which is equal to n to the log base 2 of e, which we can see is less than n cubed. And we're done. We've shown the existence of a subspace such that partitioning S according to that subspace yields max load at most 4 log n over n. 4 log n over log n. Well, I kind of swept this key lemma under the rug, right? So this is sort of the crux. We're able to square at every step. So how do we show this? Well, let's go to the ith time step and let's see what we're working with. I'm going to define this following quantity, S sub I of x, to equal the number of elements in S that's in the shift of V sub I. That's in the X shift of V sub I. In English, you can think of it as the number of balls that's in X's bin, the bin containing X. So with this, notice that the ith potential is simply the average of the exponential of s sub I of x. Great. So this lemma wants to relate the I plus first potential to the ith potential. So it's natural to try to relate s sub I plus 1 to s sub I. So to do this, let's look at a toy point, this diamond. What is s sub I of diamond and s sub I plus 1 of diamond? Well, s sub I of diamond is 1, as we can see pictorially here. It's going to be the number of balls in the bucket containing the diamond. And then now s sub I plus 1, we look at the I plus first time step. This diamond now has 2 balls. How did we get 2? Well, from the I to the I plus first time step, the diamond, the bucket containing the diamond, merged with whatever bucket you got when you shifted by the Brown vector, right? And so this bucket, which contains diamond plus W, contains 1 ball as well. And so now, at the I plus first time step, both of these buckets combined, and so we got 1 plus 1 equals 2. So in general, what we can say is that at the I plus first time step, the number of balls in X's bin is equal to the number of balls that was in X's bin plus the number of balls that's in X plus W's bin, right? Again, this is because at the ith time step, we're gluing together 2 bins. We're gluing together the bin containing X with the bin containing X plus W. Great. So this motivates us to define this auxiliary quantity, psi sub I, which is basically phi sub I expressed in terms of s sub I minus 1. Okay, it's this quantity. And what we've just shown is that when W sub I plus 1 is not in V sub I, they're the same quantity. Thus, we have the average outside of V sub I of phi sub I plus 1 is equal to the average outside of V sub I of psi sub I plus 1. Great. So now let's just expand this latter quantity and try to express it in terms of phi sub I. So again, just for a reference, this is the definitions and what we've just shown. So yeah, let's expand this out. So psi sub I plus 1, right? We know it's equal to the expectation over x and w of this quantity, L to the s of I of x plus s sub I of x plus w. But now I'm stuck. I mean, this quantity, I don't really know how to work with it anymore. In fact, probably what's very annoying is that x and w are averaged over different terms. And this is preventing me from using its symmetry. So in fact, if w was also over all of f2 to the u, we can actually simplify this a lot, right? So imagine we had it equal to f2 to the u, right? So let's say we were averaging psi over all of f2 to the u. Then with the same manipulation we get here. But now we can use the fact that if x and w are uniform over f2 to the u, uniform and independent over f2 to the u, then so is x and x plus w. Okay. This is basically because if x and w are linearly independent, so is x and x plus w. So because of this fact, we can actually, the average doesn't change if we replace x plus w with w. And then now, we now have the expectation of a product of 2 terms, which are independent, and so we can turn it into the product of the expectation. Each factor is simply phi sub I. And so we get that actually the global average over all of f2 to the u of psi is equal to phi sub I squared. If only it was averaged over all of f2 to the u rather than f2 to the u without phi sub I. So how can we solve this? So how can we get something about the average of W not in V sub I? Well, maybe we could show the average inside V sub I is larger than V sub I squared. That would then imply the average outside of V sub I would be less than V sub I squared in order to compensate so that the global average is V sub I squared. So maybe let's try to show that. So again, here's some reference. And now let's say we're at time step V sub I. And now let's say W sub I plus 1's in V sub I. So one thing we might ask is, let's say X is in some bin. What bin will X plus W be in? And the claim is that it'll be in the same exact bin. Okay? So in particular, if I take any point and then I add W to it, the resulting point is going to be in the same exact bin as the original point. And actually, the reason is just because X plus W plus VI is equal to X plus VI, right? In other words, this equality is saying the shift containing X is the same as the shift containing X plus W. And this equality is true because VI is a subspace and W is an element of VI. Thus, V sub I is equal to V sub I plus W sub I plus 1. And this equality holds. Therefore, for any X and X plus W are in the same bin. As a corollary of this statement, we have that for any W sub I plus 1 in V sub I, the number of balls in the bucket containing X is the same as the number of balls containing X plus W, because it's the exact same bucket. With this equality, we now can analyze psi sub I. Psi sub I plus 1 is going to equal, by definition, this expression. But now this latter term is equal to the former term. So we have that the exponential is just 2si of x. And now using convexity of the square or Cauchy-Schwarz, we can lower bound this by taking out the square as follows. And then now the term inside the square is just V sub I. So boom, we have for every W sub I plus 1 in V sub I, psi sub I plus 1 is greater than or equal to phi sub I squared. And this gets us what we want, and we can finally finish. In particular, we've now shown the global average of psi sub I plus 1 is phi sub I squared, and we've shown the average within V sub I is greater than or equal to phi sub I squared. Therefore, the average outside of V sub I of psi sub I plus 1 is at most phi sub I squared. And then we show that that quantity is just equal to phi sub I plus 1. Hence, we've finally shown the average over W not in V sub I of the I plus first potential is at most the ith potential square. And thus, this concludes the proof of existence. So in our paper, we show something much stronger. So we actually show the maximum load exceeds C times the optimal max load with probability at most order 1 over C squared. So actually, this statement is stronger than expected max load. Furthermore, we're able to show even when we don't have n balls and n bins, if we have m balls and n bins where they're distinct numbers, we can show, again, with probability 1 over C squared, you'll be greater than C times the optimal max load, aka whatever max load you get when you hash m balls to n bins via a random map. Also, when m is large enough, much larger than n, we can even show that each bucket, every single bucket, will be upper and lower bounded by some constant times m over n with high probability. So we're getting two-sided bounds as well. And in terms of open questions, one interesting question is, can we generalize this to FP, where P is not equal to 2? More or less, approximately the best sort of max load we know over FP is like log n raised to the log base 2 of P. So we don't even get a near logarithmic quantity, even for P equals 3. That's a very interesting question. And then another question is, can we de-randomize this hash family? In the sense, can we find a smaller family of linear maps that attain optimal max load? This current, using all linear maps, gives you a family that uses log squared n random bits. Our work implies the existence of a polynomial number of linear maps that gives you optimal max load, but this is not explicit. So it'd be very interesting to make this explicit. Thank you for watching.